Hello and welcome back to this video tutorial on non-invasive biomarkers measurement by electromagnetic means. After having seen the basic theory in part 1, here in part 2 we will discuss some practical hints for real implementation. And to do that, we will use the example of a particular application. In this case, we selected glucose concentration measurement, which is of great interest for managing diabetes. So let's try to implement one of these sensors, one of these measurement systems. And well, we saw the interest of using microwave resonators as sensors. So here in electromagnetic simulation software HFSS, we have designed a microwave resonator to act as a sensor. You can use any other usual electromagnetic simulation software such as CST Studio or COMSOL Multiphysics. For this particular case, we designed two input and output lines tuned at 50 ohms to have matched measurements, and then we coupled the resonator in the middle. We selected an open loop resonator, split ring resonator, and we used a usual substrate with a permittivity, a real part of the permittivity of 6.0 and a loss tangent of 0.02, which means very low losses. We tuned the length of the resonator in order to have a resonance frequency with no load of 9.2 gigahertz. And finally, we want to make some simulations of this system when we have a sample upon the resonator, and we can change the properties of the sample to see the associated changes in the response of the sensor. As a very simplified case, we can model the sample just as a box of material, and we can change the properties of this material. So once we are happy with the design, we are ready to make all the simulations. We want to make a parametric study including several values for the real part of the permittivity of the sample and the imaginary part or loss tangent of the sample. To do that, in this software, you right-click on optometric option and then you add a parametric setup. In other softwares, of course, you will find similar options. Then you are able to select the parameters that you want to sweep, to change their values and make different simulations with different values. First of all, we will change the values of the real part of the permittivity of the sample, and we can manually enter several values, such as, for example, 1, 6, 20, etc., up to 80. For this example, I selected values within a huge range just to show the behavior. For a more particular example, you can select a more redefined range in order to have more precision in your range of interest. And then we repeat these steps in order to include a second parametric setup and change the values of the loss tangent of the sample. I again selected values in a long range in order to see the full behavior. So we run all these simulations, we let the computer work, and then when all the simulations are finished, we retrieve the response of the sensor for each simulation. We see the resonance peak for each simulation, and we compute our indicators from each response of the sensor. In this case, just for brevity, we are only analyzing the resonance frequency against the real part or the permittivity of the sample, and the unloaded quality factor against the loss tangent of the permittivity against the loss tangent of the sample. In both cases, we can easily identify interesting measurement regions in which we have a very sharp slope of the curve, which means high sensitivity, which means high resolution, because in these regions, for example, for the resonance frequency, in the regions of values of the real part of the permittivity between 0 and approximately 10, we can say that a very small change in the real part of the permittivity of the sample will be seen as a noticeable, remarkable change in the resonance frequency of our sensor. And a similar behavior we can see for the unloaded quality factor. So now we need to see which are the usual values of the real part of permittivity and loss tangent of the sample in our targeted samples. In this case, as a simplification, we will try to measure the glucose concentration in pure water solutions, which is a simplified case of blood, since blood is made of about 70%, 80% of water. So fortunately, the dielectric properties of water have been widely characterized in the literature, and we know the values of the real part of permittivity and loss tangent of water for each temperature and for each particular frequency. So it would be great that the real part of the permittivity of water would have a low value, so that we would be in our region of interest. So let's see which is the real value. Well, we were unlucky this time. The idea was a good one, but as you can see, this is maybe not the best approach. So let's see what happens with the other parameter. Let's see which is the usual values of water at this frequency for the loss tangent. Okay, this is different. This is what we were looking for. So now we have a reason to select the unloaded quality factor as the measurement parameter for this particular application. Of course, there will be other applications for which the resonance frequency will be of higher interest, and you can also analyze other parameters, other indicators from the response of the sensor. But for this particular application, this is the interesting one. So we will optimize our design in order to have variations in the unloaded quality factor, and we will select this measurement approach. We can arrive to the same conclusion from a more theoretical point of view. For example, we can go back to the simple theoretical model of the microwave resonator, in which we have included the contribution of the presence of a dielectric sample, such as water. As it is not a magnetic sample, we are not foreseeing any impact in the inductive part, so the inductance remains unchanged, but the resistive part and the capacitive parts now are defined as a sum of two contributions: the contribution associated to the line and the contribution associated to the presence of the sample. Here we can remake the calculations, we can obtain the new expressions for the resonance frequency and the unloaded quality factor, and then I propose a couple of approximations. We can assume that the sample will have a very high value of the real part of the permittivity, which is true if you see it in the previous slide, and also the sample will have high losses, high dielectric losses, which is true as long as we use low losses substrate and a good conductor. If we apply these approximations and we apply the definition of the loss tangent of the sample in terms of the elements in the circuit, then we arrive to this simple equation in green that says that the unloaded quality factor is approximately equal to 1 over the loss tangent of the sample. This is again a good reason to select the unloaded quality factor as the base for this measurement system. In addition, for this particular case, we know that water glucose solutions below 15 gigahertz, which is true in our case, in these cases, for the same change in the glucose concentration, we will see a positive change in the imaginary part of the permittivity and a negative change in the real part of the permittivity. This means that the same change in the glucose concentration leads to opposite changes in the imaginary part and the real part of the permittivity. being the unloaded quality factor directly related to the loss tangent of the sample, and being the loss tangent of the sample defined as the quotient between the imaginary part and the real part of the permittivity. When we have opposite trends in the imaginary part and the real part of the permittivity, the evolution, the change of the loss tangent of the sample is even more noticeable, and therefore the changes in the unloaded quality factor of the resonator will be even more noticeable. So from any point of view, we can arrive to the same conclusion: the interest on using unloaded quality factor based sensors for this particular application, that is glucose concentration sensing. In general, we have seen in this second part the interest of micro-resonating unloaded quality factor based sensors as instruments for biomedical applications. The main advantages include significant penetration depths in living matter and also high sensitivity to variations in the main relaxation processes of aqueous systems, and of course non-invasive capabilities. In addition to usual benefits from microwave circuitry, such as compatibility with planar technology, ease of integration, small sizes, and cost effectiveness. These sensors will face in the near future two main challenges: increasing the sensitivity and increasing the selectivity. While recent works have shown interesting techniques to remarkably increase the sensitivity, in my opinion, the real challenge for the future will be the improvement of the selectivity, which is an intrinsic limitation of these sensors. That is, the ability to discern variations of different components at the same time in the sample. So now, based on all these principles, we will see a couple of successful studies. For example, these ones made use of single microstrip split ring resonators with a small sample holder, and these sensors were proved effective for the measurement of glucose concentration in both aqueous and human blood solutions, with good linearity and acceptable sensitivities. Going a step beyond, implementations have been proposed using certified biocompatible materials ready to be used for biomedical applications. In this particular case, an implementation based on inverted microstrip with a single split ring resonator having air as virtual substrate was proposed, and it was proved effective for increasing the sensitivity remarkably. We can see that the results show good linearity, good sensitivity, high enough to discern very low quantities of glucose concentration of interest for the diabetes domain. This sensor could even undergo a clinical test, the Clark error grid test, which is one of the usual tests made to measurement instruments for the management of diabetes. Of course, the final whole instrument will need to be portable, will need to be used out of the laboratory, so we can build the final measurement instrument using several approaches. For example, here everything started from the microcontroller unit, which fed a voltage control oscillator with a ramp voltage signal with increasing voltage values. At the output of the voltage control oscillator, what we have is a sinusoid signal with increasing frequency, which is what we are interested in. Of course, the signal must be filtered to avoid harmonics, and then thanks to a directional coupler, we can have a copy of the original signal and we can store the copy for comparison. The other copy of the signal is driven to the device under test, that is the sensor, the microwave resonator, and then the signal coming from the sensor after measurement is stored and compared to the original reference signal that we stored previously, and the difference is computed and introduced into the microcontroller unit in order to make the calculations, retrieve the indicators from the sensor, and retrieve the final values. This is one example of how to implement the final measurement instrument. These instruments were installed and tested in clinical settings. Talking about the sensitivity, there are techniques that lead to remarkable increases of the sensitivity. Up to now, we only saw sensors including one single resonator, but it was proved that using mutually coupled resonators leads to increases of the sensitivity of the unloaded quality factor of almost 300%, 298% to be exact, with respect to the single resonator case. So these techniques are under study right now, and they raise as highly interesting in order to have a real improvement of the sensitivity. And finally, the selectivity is, in my opinion, currently the main challenge for these sensors. Several approaches have been recently published and are currently under study. For example, we can still use several coupled resonators, but not only to increase the sensitivity, but we can make the most of them by analyzing the different resonance peaks, the different resonance frequency, quality factors, and so on, so that we can obtain multiple indicators from the response of the sensor that can be related to multiple parameters from the sample. Other approaches propose the use of several frequency measurement points so that we can separate effects in the sample appearing at low frequencies and effects in the sample appearing at high frequencies. So this is an open field of research currently, and we expect advancements in the near future in order to be able to better discern only the quantities that we are interested in. And that was all. Thank you very much. I hope you enjoyed this video tutorial on non-invasive biomarkers measurement by electromagnetic means. I am Carlos Juan from Miguel Hernández University of Elche, and it was a pleasure.